Hi to all. In this video, we are going to see about design of stator windings. Turn per phase. EMF equation of an induction motor is given by E phase is equal to 4.44 F by T phase kW. Hence, turns per phase can be obtained from EMF equation. T phase is equal to E phase divided by 4.44 F by kW. Generally, the induced EMF can be assumed to be equal to the applied voltage per phase. Okay, so flux per pole is equal to BAV into pi dl by P. Winding factor Kw may be assumed as 0.955 for full pitch distributed winding unless otherwise not specified. If they are not specified, we should take as a 0.955 as the winding factor Kw. Okay, number of conductor per phase. Z phase is equal to 2 into T phase. Otherwise, T phase is equal to Z phase by 2. And hence, total number of stator conductors Z is equal to 6 phase. Okay. And conductors per slot Zs is equal to Z by Ss or 6 T phase by Ss. Where Zs is the integer for single layer winding, even number for double layer winding. Conductor cross section. Area of cross section of the stator conductor can be estimated from the stator current per phase and suitably assumed value of current density for the stator winding. Sectional area of the stator conductor AS is equal to IS by del S, where del S is the current density in stator winding. Stator current per phase IS is equal to Q by 3 V phase cos phi. Okay. A suitable value of current density has to be assumed considering the advantage and disadvantage. Okay, the advantage of high value of current density, reduction in cross section. Okay, if we supply a current, more current in a conductor, so that is current density will be more than the cross section, reduction in cross section, reduction in weight, and reduction in cost. Disadvantage of high value of current density, increase in resistance, increase in copper loss, increase in temperature rise. Okay, reduction in efficiency. These are the disadvantages of high value of current density. Hence, higher value is assumed for low voltage machines and small machines. Usual values of current density for stator winding is 3 to 5 amps. Based on the sectional area, shape and size of the conductor can be decided. If the sectional area of the conductor is below 5 mm square, then usually circular conductors are employed. The sectional area of the slot will be 5 mm. Conductor size, if it is 5 mm, less than 5 mm, then we should go for uh, circular type of conductors. Then usually circular conductors are employed. If it is above 5 mm rectangular, then rectangular conductors will be employed. Standard size of round and rectangular conductors can be selected by referring the tables of conductors given in design data handbook. In case of the rectangular conductors, width of thickness ratio must be between 2.5 to 3.5. Okay, here you can see the different types of conductors. Okay, stator coils. These are the stator coils and placed in a stator. This one. Okay, here if the stator slot will be less than 5 mm, then we should go for a round type conductor. If the distance, that is slot size, is more than 5 mm, then we should go for rectangular conductors. Okay, length of the main turn. Length of the main turn is calculated using an empirical formula. Okay, LMT is equal to, length of main turn is equal to 2L plus 2.3 TP plus 0.24, where L is the gross length of the stator and TP is pole pitch in meters. Okay. So resistance of stator winding. Resistance of the stator winding per phase is calculated using the formula 0.021 multiplied with LMT multiplied with T phase by AS, where LMT is, is in meter and AS is in millimeter square. Using calculated resistance of stator winding copper loss is in stator winding can be calculated as, okay, the total copper loss in stator winding is equal to 3 Is square into Ts. Flux density in stator tooth. Okay, knowing the dimension of stator slot pitch, width of the slot and width of the stator tooth, flux density in the stator tooth can be calculated. The flux density in the stator tooth is limited to 1.8 Tesla. It should not go beyond 1.8 Tesla. As the stator tooth is tapering towards the bottom, the flux density is calculated at 1 by 3/3 height from the narrow end of the tooth. The flux density at 1 by 3rd height from the narrow end of the tooth can be calculated as follows. Diameter at 1 by 3rd height from narrow end. D is equal to D plus 1 by 3 x HTS multiplied with 2. Okay. Slot pitch at 1 by 3rd height is equal to T into multiply S is equal to pi into D by S suffix S. Tooth width at this session is equal to BT. Tooth width is equal to T dash S minus BS. Okay. Area of one stator tooth is equal to AT is equal to BT into LI. Area of all the stator tooth per pole AT is equal to BT into LI multiplied with number of teeth per pole. Okay. Mean flux density in stator teeth BT is equal to pi by AT. Maximum flux density in the stator teeth may be taken to the less than 1.5 times the above value. Depth of stator core below the stators. There will be a certain solid portions below the slots in the stator, which is called the depth of the stator core. This depth of the stator core can be calculated by assuming suitable values for the flux density Bc in the stator core. Generally, the flux density in the stator core may be assumed varying between 1.2 to 1.4 Tesla. Depth of the stator core can be calculated as follows. Flux in the stator core section pi c is equal to 1 by 2 pi. Area of stator core AC is equal to pi by 2 BC. Area of stator core AC is equal to Li multiplied with DCS. Hence, depth of the core is equal to AC by Li. Using the design data obtained so far, outer diameter of the stator core can be calculated as D0 is equal to D plus 2 HSS is equal to 2 DCS, where HSS is the height of the stator slot. Okay. Thank you.